Hello and welcome back to Crystallography for everyone. In the last video, we saw the concept of a unit cell, an object that will fill all space when translated by the lattice translation vectors. We looked at an example of a centered rectangular cell or lattice and the parallelogram cell, also the primitive cell for this particular grid of lattice points, which, remember, contains one lattice point per cell. Centered rectangular cell contained two, which is a non-primitive cell. In this video, we're going to look at an example that is going to tie together many of the concepts that we've already looked at. The concept of a lattice with a basis and drawing unit cells. This problem asks us to take a 2D crystal with a rectangular lattice having lattice parameters A equal to 1.5 angstrom, B equal to 3 angstrom. Just to remind you, 1 angstrom is 10 to the minus 10 meters. This is a convenient unit for the atomic scale. This crystal has a 2-atom basis with an atom I'm calling S at 0, 0, and an atom I'm calling P at 1/2, 1/2. This problem asks us to draw the crystal, show the lattice translation vector R, and then annotate the crystal directions and show one valid unit cell and one invalid unit cell. So we're going to use that definition of the unit cell from the last video. At this point, I believe you can solve this problem on your own if you've been going through each video. So if you would like to do that, I would pause the video here and then come back. I think the first thing we should do here is draw the lattice translation vector R. And so we can remember the definition for a rectangular lattice. It's going to have some vector A plus some vector B. And this is arbitrary. This is just the way we've been working through these problems. And if I define, again, my axes, so this direction is X and Y, our lattice translation vector is going to be A, which is given, times X hat, the X direction, a unit vector, plus B times Y hat. And I will draw this vector on our lattice that I have, or our rectangular grid that I've put in here ahead of time. So we have our two vectors here. This guy is A, and this guy is B. I should note that for this to be the general lattice translation vector, we'll have U and V as prefactors for the A and B vectors, where U and V are integers. So this symbol here, I don't think I've used it yet in this series, means that U and V are a member of the set of integers. So they can go from minus infinity to positive infinity in steps of 1. You could be 0, 1, 2, 3, minus 1, minus 2, minus 3, etc. Just to be as clear as possible about that. So we have our general lattice translation vector. And in effect, we have also annotated our crystal dimensions. So the magnitude of A, the vector A, is just A. The magnitude of B is just B. So that effectively defines the dimensions of our crystal. At this point, I think we should draw the rest of the crystal. So I will use this color for the S atoms, and I will use this color for the P atoms. The S atoms are at 0, 0. And if you remember from one of the previous videos, 0, 0 essentially refers to any of the lattice points. So the P atoms will fall directly on the lattice points. From the definition of our lattice, if we're going to call this point 0, 0, we can also call the point over here 0, 0, and any other point in the lattice. So I will just draw 9 of these points here. For time, I'll just draw the 9, but we remember that this extends off in all directions on our 2D plane. The P atoms lie at 1/2, 1/2. The 1/2 is going to refer to 1/2 of A and 1/2 of B, the lattice translation vectors. So what I can do is bisect each vector here and move 1/2 in A in the X direction, 1/2 in B in the Y direction, and that is where my first P atom is going to fall. Remembering the concept of a basis, our basis is assigned to each lattice point, which is this rectangular grid. So we can continue this logic and put a P atom in the center of each set of 4 S atoms. And this will continue to infinity. So at this point, we've drawn our crystal. We've shown the lattice translation vector R, the general lattice translation vector. We've annotated our crystal dimensions. And now we can start looking at the different types of unit cells that we have here. I think that the most obvious one would be a rectangular cell, which I will draw here in green. So you can see that this cell will fill all space if we move it around according to our general lattice translation vector that we've defined over here. So if I take this point as the 0, 0 point and start moving that around, say, move it up 1 in A and B, we will get another unit cell here. And if we were to put in every possible value for U and V, an infinite number of values, we would fill all space with these unit cells. It's important to note, this is a rectangular unit cell. In the last video, we saw a centered cell, a centered rectangular cell. This is not a centered rectangular cell. There is no lattice point in the center of this cell, and thus it is not a centered cell. This point is the basis atom. And that's an important thing to consider. In the future, when we're working in 3D, we will have a body-centered cubic cell, which would be somewhat analogous to this, except for in 3 dimensions, where this point would be in the center. In that case, it will be a lattice point, and we'll go through some examples with that. In this case, it's a rectangular cell. It just happens to have a basis atom in the center. That's a real semantic way of looking at things, but it is important in crystallography. I'll draw another valid cell just because I can, and to try and demonstrate that the concept of the unit cell is very arbitrary. We could decide to switch the position of each atom, and we would have the same sized cell, same dimensioned cell, except for the p atoms would now be at 0, 0, and this cell could also fill all space. The problem also asks us to draw an invalid unit cell, which I can see here already. That would be this one, which looks like the parallelogram cell that we saw in the previous example, but it isn't. It isn't a valid unit cell at all. The reason for this is that each corner of the unit cell should fall on a lattice point. And that was okay in the previous video, in the previous example, because each lattice point was the same atom. In this case, if we were to draw this cell, we would have a p atom on this lattice point and an s atom on this other lattice point. This completely breaks our definition of a lattice that each point is indistinguishable. This point would not be the same as this point any longer. So this would not be a valid unit cell. I think in the next video we will look at another example similar to this, perhaps go a little quicker through that one, and then we will start working through 3D examples.